Somewhere in a basement archive, there are more than 500,000 clay tablets that no living human can fully read. They were written before the pyramids of Giza were finished, before the Trojan War, before the alphabet you're reading right now even existed. And for over a century, only a tiny handful of scholars on the entire planet could decode them. That number was so small that if every qualified expert in Cuneiform script disappeared tomorrow, we'd lose access to a huge chunk of the earliest written record of a human civilization. But in the last 3 years, something changed. Machines started reading what humans could barely touch. And now researchers are asking a much stranger question. What happens when you don't just throw artificial intelligence at these texts, but quantum computing too? Stick with me, because what's happening right now in this field is one of the strangest collisions of ancient history and cutting-edge technology you'll see anywhere. And by the end of this video, you'll understand exactly where the real breakthroughs are, and where the hype starts to outrun the evidence. Let's start with the basics, because you need to understand just how hard this problem actually is. Cuneiform is one of the oldest writing systems ever discovered, dating back to around 3400 BCE in Mesopotamia, the region that today covers parts of Iraq and Syria. It wasn't written with a pen and paper. Scribes pressed a cut reed into soft clay, leaving behind wedge-shaped marks. That's actually where the name comes from. Cuneus is Latin for wedge. Over thousands of years, this script was used to write multiple languages, most famously Sumerian and Akkadian. Sumerian is especially important because it's considered a language isolate, meaning it's not clearly related to any other known language family on Earth. There's nothing to compare it to. No sister language to lean on for shortcuts. Now imagine trying to read a document written in a language with no living speakers, using a script that changed shape and style depending on the region, the era, and even the individual scribe's handwriting, carved into a physical object that's often cracked, chipped, or partially destroyed. That's the daily reality for Assyriologists, the scholars who specialize in this field. And here's the number that should stop you in your tracks. Researchers estimate there are literally hundreds of thousands of these tablets sitting in museum collections around the world, and only a few hundred trained experts worldwide who can read them fluently. At the current pace of manual translation, some of these texts were realistically never going to be read in our lifetimes. That's the wall the field had been stuck behind for decades. And it's exactly the kind of wall that machine learning is built to break through. But the first real crack in that wall didn't even come from Mesopotamia. It came from Greece. In March 2022, a team from Google's DeepMind, working with Kalfaskari University of Venice, Oxford, and the Athens University of Economics and Business, published a paper in the journal Nature, describing a deep neural network they called Ithaca, named after the island home of Odysseus. Ithaca wasn't built for Sumerian or Akkadian. It was trained on ancient Greek inscriptions, carved into stone, pottery, and metal between the 7th century BCE and the 5th century CE. Its job was to do 3 things at once: fill in missing or damaged sections of text, estimate where the inscription originally came from, and estimate when it was written. And the results were genuinely striking. Working completely alone, Ithaca restored damaged texts with 62% accuracy. That alone would have been impressive. But here's the number that mattered even more. When historians used Ithaca as a collaborator rather than a replacement, their own accuracy on the same task jumped from 25%, working solo, all the way up to 72%. The AI wasn't replacing the expert. It was making the expert dramatically better. And it could also correctly identify the geographic origin of an inscription 71% of the time, and date it to within about 30 years of the true range. Ithaca has already been used to help redate inscriptions from the Athenian Acropolis and contribute to ongoing academic debates about classical history. That was the proof of concept the entire field needed. If a neural network could do this for ancient Greek, the obvious next question was, what about the language that came even earlier? What about Sumerian and Akkadian, the languages that predate Greek by thousands of years? The question didn't stay unanswered for long. Just over a year after Ithaca made headlines in May 2023, a team led by Guy Guthers, along with Shai Gordon, Louis Saenz, Omer Levy, and Jonathan Barant, researchers from Tel Aviv University and Ariel University in Israel, published a study in the peer-reviewed journal PNAS Nexus. Their model attempted something Ithaca never tried: full translation, not just restoration. They trained a neural network to translate Akkadian cuneiform directly into English, using 2 different approaches. One version worked from the Unicode symbols of the cuneiform signs themselves. The other worked from transliterations, the Latin alphabet representation scholars typically use as a middle step. To measure quality, they used something called a BLEU4 score, a standard metric in machine translation that ranges from 0 to 100, where 100 would be a flawless, human-perfect translation, a score no real system, human or machine, actually reaches. Their transliteration to English model scored 37. 47, their direct cuneiform to English model scored 36. 52. For context that actually matters here, Guthers himself pointed out that Google Translate, going from Spanish to English, two closely related, massively resourced modern languages, scores around 60 on that same scale. So a first-generation model translating a 4,000-year-old dead language wasn't beating Google Translate. But scoring in the high 30s on a task nobody had ever automated before was, by the team's own description, a genuinely strong result, especially for shorter and medium-length sentences under about 118 characters. Guthers described the feeling of using it this way, that he didn't need to understand Akkadian at all to get a sense of what a tablet was actually saying. Think about what that means. For the first time, someone with zero training in a dead language could get a rough but usable window into a document written before recorded history, as most of us think of it. But translation was only half of the puzzle, because Akkadian isn't even the oldest language hiding in these tablets. Sumerian is older still, and it turned out to be a much harder mountain to climb. Here's the part most coverage of this story leaves out, and it's important because it's where honesty matters most. Sumerian has lagged behind Akkadian in this AI revolution, and there's a very specific reason why. Akkadian had a massive advantage. Decades of digitized, transliterated texts already sitting in structured databases, ready to train a model on. Sumerian didn't have that same foundation, at least not at scale. That gap started closing in 2024, when researchers released a dataset called SumTablets, pairing digital Unicode cuneiform signs with scholarly transliterations across more than 91,000 Sumerian tablets. That dataset alone didn't produce a working translator, but it built the training ground one would eventually need. Then in 2025, a research initiative called EvaCun tested language models specifically on Sumerian and Akkadian tasks, things like identifying the correct dictionary form of a word, or predicting missing, damaged portions of a text. These tasks sound small. They're not flashy like a full English translation. But scholars will tell you this repetitive reconstruction work is exactly what eats up years of a human researcher's career. Automating even part of it is a real, practical win, even if it doesn't make for a dramatic headline. And the most recent development on record happened just last month, in July 2026, when a project called TabletCraft introduced something new, a bidirectional translation model trained on 116,000 Akkadian English example pairs. What made it different from the 2023 system wasn't just scale, it could also work in reverse, translating English into Akkadian and rendering that output back into cuneiform script. That's a meaningful shift, because it opens the door to interactive tools, not just one-way academic translation. So where does that leave us as of today? We have real, published, peer-reviewed progress on Akkadian translation. We have growing infrastructure for Sumerian, even if a complete, reliable Sumerian to English translator at Akkadian's level still doesn't fully exist yet. And we have models getting better at the unglamorous but essential task of filling in the gaps in damaged texts. That's the honest state of the field right now. But there's a bigger, stranger question circling all of this, one that brings us to quantum computing. And this is where you need to slow down and separate what's actually proven from what's still speculation. You've probably seen headlines claiming quantum computers are about to revolutionize language AI. Some of that is genuine research. A lot of it is marketing dressed up as science. So let's be precise about what actually exists. There's a real active academic field called quantum natural language processing, or QNLP for short. It first appeared in research literature back in 2016, and the first dedicated conference on the topic happened in 2019. The core idea is fascinating, even if it's abstract. Instead of representing words as strings of numbers the way classical AI does, QNLP represents words and grammar as quantum circuits, drawing on a mathematical framework from an area of physics called categorical quantum mechanics. In theory, this could eventually let quantum computers process certain language patterns in ways that scale differently and potentially faster than classical computers for very specific types of problems. Researchers have already run early experiments on real trapped ion quantum computers, testing things like topic classification and resolving ambiguous sentence meanings. There's even a Python library built for exactly this kind of experimentation that researchers around the world have used to test these ideas hands-on. So this isn't science fiction. It's a legitimate, growing research field with real papers, real conferences, and real hardware experiments happening as recently as this year. But here's where you need to keep your expectations grounded and where honest framing matters most. As of right now, there is no published, peer-reviewed research showing a quantum computer translating Sumerian, Akkadian, or any ancient cuneiform language. None. The QNLP field itself is still described by the researchers working in it as small and early stage. One detailed survey of the field found only a few dozen relevant papers across the major academic databases combined. Quantum hardware today is still limited by noise, error rates, and a small number of usable qubits, which means most current QNLP work is happening on narrow, controlled tasks, not sprawling, messy, ambiguous ancient texts full of missing fragments and regional dialects. Experts in the field are genuinely divided on the timeline here. Some argue quantum approaches could eventually help with exactly the kind of deep ambiguity that ancient languages are full of. Words with multiple possible meanings, grammar structures that don't map cleanly onto modern languages, the way classical AI sometimes forces a best guess where a true structural understanding would work better. Others argue that quantum computing's near-term advantage, if it exists at all for language tasks, may end up limited to fairly narrow classification problems, not full-scale translation of anything, let alone something as fragmentary as a 4,000-year-old broken tablet. So when you see a headline claiming quantum computing is about to crack ancient languages wide open, what you're really looking at is a real promising research direction, dressed up in premature, overconfident language. The technology to combine deciphered Sumerian datasets with quantum language models doesn't exist yet in any demonstrated form. It's a genuinely exciting possible future. It is not a current reality, and that distinction is exactly what most coverage of this topic gets wrong. So where does this actually leave us right now in 2026? Classical AI has already done something remarkable and verifiable. It has taken a translation task that used to require years of specialized training and made a rough, usable version of it accessible to a computer scientist with zero background in ancient Mesopotamian languages. It has helped historians restore Greek inscriptions with accuracy nearly 3 times higher than working alone. It has produced working, peer-reviewed Akkadian translation systems, and it is actively closing the gap for Sumerian through new datasets and shared research challenges released as recently as this year. None of these systems are perfect. None of them replace trained Assyriologists. In fact, every major study on this topic makes the same point again and again, that the strongest results come from AI and human experts working together, not AI working alone. And quantum computing sits one layer further out on the horizon. A real field, with real early results on other language tasks, but with no demonstrated breakthrough yet on ancient scripts specifically, and genuine open disagreement among researchers about how fast that could change. If you found this kind of story interesting, this channel covers exactly this intersection of ancient history and modern technology on a regular basis, so consider subscribing if you want to keep following where this goes. There's something almost humbling about all of this, if you sit with it for a second. 4,000 years ago, someone pressed a reed into wet clay to record a debt, a prayer, a piece of law, or a story, never imagining that their words would outlast their entire civilization by thousands of years. And now in an age of neural networks and quantum circuits, we're building tools whose entire purpose is to listen to that voice again. Not to speak for it, not to guess at it carelessly, but to help a small number of human experts finally catch up to a backlog of history that's been waiting patiently in the dark for someone or something capable of reading it. We're not there yet. Not completely. But for the first time in over a century, that gap is actually closing. And if you want to see where it goes from here, hit like on this video and stay subscribed because this story is far from finished.